So, to start with who we are two students at Copenhagen Business School, finished graduating from our masters, and basically what I'm going to present is our master thesis, and it's in some ways still embryonic research because we were doing it just for a couple of last months. So it's just like I'll present the results up to date, what we have so far. So what is it all about? We show that business cycles can emerge in the economy just because how people act in the economy, how people think, how people rationalize, how they process information. They help to make decisions about future, to make investment decisions, to make decisions about hiring and decisions about production. And we show that it can cause economic instability without any shocks to productivity or economic fundamentals whatsoever. So a bit of background, idea that expectations can drive cycles is not new, and it was first probably suggested by Artur. He said that fluctuations may arrive just because entrepreneurs do not invest optimally, and because of their wrong expectation they invest wrong amount of resources. And then it's evolved probably to notion of animal spirits in John Maynard Keynes' general theory. But after that we all know that what happened to economic theory was called rational expectations revolution. They basically assumed that that was a modeling framework would make all the agents optimize their lifetime utility and lifetime profits as though they have perfect foresight and know how economy functions exactly. What did it bring to economics? It bring very powerful modeling technique, and it's really led to various applications of math to economics to flourish. On the other hand, in the environment with perfect foresight, it was very hard to obtain endogenous fluctuations, because it's very hard to make system unstable in which agents have know everything which is going to happen basically. So what it led to? It led to appearance of real business cycle theory, which basically derived fluctuations and instability from external shocks to economic fluctuations. Originally, it was shock to total factor productivity. Not to say also, I have to say also that learning expectations were also applied to explain business cycles. But what was mainly done is just we take authors took pure RBC model with a shock, and then just show that learning expectations may make fluctuations be bigger with higher amplitude, longer, and better represent real life, what we observe in real life. Still, we perceived it as not enough, and we wanted to show that the economy may fluctuate without any shocks whatsoever. And our motivation was first of all to diverge from dynamic stochastic general equilibrium models to say switch off the God regime and inhabit our theoretical model with living creatures which are not perfect astrologists, and for a caster they do not know basically what's going to happen. They guess and they do the best they can to foresee the future. We, as I mentioned, we have no shocks in our model, and also we try to follow the KISS principle. We try to build a very simple, small, and compact model that easy to track what's going on, instead of trying to model a mastodon that is very hard and counterintuitive to understand. So today I am just only going to present a simple model. The basic setup is that we have a growth-less economy, which they are living they're functioning n identical firms and age identical households. Agents all the agents, both firms and households, perceive themselves to be too small to affect economy. Basically, in case of firms, it means that they are price takers. They observe price on the market and then adjust to it instead of like thinking how they can change it. We also make an assumption of homogeneous output that is used for both as consumer and capital goods. So there is just like one homogeneous steel that everybody eats, everybody uses as iPads and whatever. We also refrain from modeling financial markets explicitly, so we just said that households provide their savings for firms to invest without any like contracted nominal interest rate. So like next periods, I will show you later how it works on the timeline. In our economy, since economy is growthless, we do not consider economic growth in our model, and therefore we made also constant money stock, which is fixed M. And also we made, for simplicity, assumption of unity velocity, so that simplified version of quantity equation of money holds. For above point to hold, we need that in each period, each household disposes exactly M over H of cash, because otherwise there will be spent either more or less in the economy, and then the quantity equation of money will not hold. That would imply that labor income and savings from previous period should equal exactly M, which leads to what we call nominal constraint, that M equals number of households multiplied by savings from previous period plus labor income, which is like nominal wage multiplied by number of firms and multiplied by LT, where LT is labor employed by one firm. So this is a timeline describing what happens within one period T. So in our model, everything does not happen simultaneously, but rather in sequence. So first of all, at the very beginning of the period, firms having their price expectation, PT expected, and like capital KT, which is basically giving to them as it's determined by household savings from previous period, they decide on how much they would like to produce for this period with this price to optimize their profits, and of course how much labor they will have to hire to make this production possible. Also, like when they make decision about production and labor, they form demand for labor, and therefore nominal wage is determined simultaneously at this stage. Then after firms produce QT, the price PT is determined on the market from quantity equation of money. When agents observe actual price outcome, they compare it with what they expected, and they update the forecasting tool or whatever the reasoning they use to form new expectations, PT plus 1 expected for the next period. By the way, a small remark, we just for simplicity we assume that households and firms have the same expectations of price. Like there is like some general expectation that market has. Giving this expectation of price, households decide on how much of their nominal income they would like to save for the next period, and then it's being invested by firms.
Artur,
Yeah.
do households own the firms? I mean, what happens to profits? Aren't they still one of the households?
I think that in this setting it basically doesn't matter, like who is the owner of firms.
Yeah, but they will receive dividends, right? They will affect their budget constantly.
Yeah, but basically, like from this nominal constraint one, it's actually happened that firms return everything they earn to the households in the end. So you can treat it as though they owe the firm. It can be like even easier to explain why they provide their savings without interest rate. So next, let's see how our firms are functioning. We assume that firms have Cobb-Douglas production technology and use two factors, labor and capital. Therefore, at the beginning of each period, when I showed on timeline, they decide on how much to produce and how much to hire, they solve a simple profit maximization problem. Solution to the problem is stated in nominal terms, so basically it said that they have to maximize their nominal income. One could argue about that, but if you just divide the whole problem by actually fixed price expectations, you will receive the same equation in real terms. Combined with nominal constraint 1, which I showed to you previously, we can get actual employment and production from solution to this problem, and we have that total economy output depends negatively, which is surprisingly, it depends negatively on the expected price. Well, even though it may be counterintuitive, but the simple explanation to this fact is that it's the result of total interactions, of like all the interactions in our model. When we just simply solve the problem for firms, what they want to produce and how much labor they want to hire, of course, positively depends on price. But once we combine it with money restrictions, it's just like the negative effect dominates. So let's have a look at our households. For simplicity, we assume that households will use logarithmic utility function and to value their real consumption and real savings expressed in expected purchasing power next period. We assume that households do not care what happens after next period, just because they are not that sophisticated in their rationing. Also, like even though assumption about logarithmic utility seems to be like too simplistic, we try to build the same model with a hyperbolic utility function, which is like the most general functional forms you can imagine, and the things still work. Just because math becomes very, I didn't want to expose you to very huge equations. Therefore, I use logarithmic utility, which provides very simple linear relations. Sure.
Why would you value current consumption in expected purchasing power?
Current consumption is valued in, I am going to this, so it is like exactly next equation. This is the maximization problem that households solve. So basically what it says that current consumption, which is nominal income minus savings divided by current price. So this consumption is valued in current purchasing power, and the second additive as savings valued in expected purchasing power. So what they save, they divide by expected price. And then we also like added constant C, since we didn't want to model income expectations explicitly, but of course households have to value savings less than current consumption, because of course they should expect some income to come next year, and therefore like starting point from valuing savings is higher than 0. So we needed to add this constant to adjust marginal utility of savings down. So solving this maximization problem yields a very simple linear form for savings, which is basically said that it positively depends on nominal income this period, and negatively depends on expected price, which basically said that savings increase in real interest rate, because the inverse thing to inflation -1 is basically what households get in real terms next period if they save. Combining solution to the firm's problem and the household's problem, we can get what is called the actual law of motion for the economy. Actual law of motion is just equation describing how, giving what agents expect, how the expectation will really feed in economy, and what will be the actual outcome. And you can see, first of all, we also substituted nominal income with M over H, as I noted before. So IT disappeared from the actual law of motion. And what you can see is that actual price outcome is not linear in expected price. If you look at this multiplier closure, which is like itself decreasing function expected price, we can see that if D is bigger than 1, then economic agents underpredict the price, which is like very easy, because if this multiplier is bigger than 1, then the actual price is higher than what they expected. When this multiplier is lower than 1, they overpredict the price, and they form the correct expectation of price only if this D equals exactly 1. Then we want to see if there is like some equilibrium state in our economy, and there is one. The equilibrium state will be exactly that when agents form correct expectations. Because if they don't form correct expectations, they will adjust their learning tool, and the system will not be fixed, of course. So the condition for equilibrium from learning perspective is that D as a function of equilibrium price equals 1. Solving that, we can just get equations for equilibrium price and equilibrium output levels in the economy.
Can you clarify what the households are learning? Which parameter is answered?
I will come to that. I will come to that a bit later. So far, to clarify, so far we didn't talk explicitly how expectations are formed. How expectations are formed in the economy. We just described how economy works once we know that expectations have been formed. So if you look at these equations of equilibrium price and equilibrium output, it's very easy to see that money is neutral in the long run. If for example, government, which is not present in our model, but if we add it, it decides to double monetary base, then equilibrium price will double in the long run. But equilibrium level of real output is completely independent from the monetary base, which makes a lot of sense. Still, there is a possibility that change in monetary base can have some short-term real effects from actual law of motion, which gives rise to possibility of monetary policy, which we'll talk about later. So, giving these equations and giving the actual law of motion of price, we can ask ourselves a question. So, is it possible for this economy to show fluctuations, or with it, like if agents have some wrong expectation, would they can just converge to equilibrium without any cycles whatsoever? And there is actually a possibility just from this simple theoretical model. As we showed before, economic agents always overestimate future prices when they are higher than equilibrium price, and contrary-wise, they always underestimate future price when they are lower than equilibrium price. Existence of these expectation errors make them learn, because they suddenly realize that what they expected is not coming true, so probably our beliefs about how economies function are not correct. Therefore, we need to update them, of course. But if we assume that agents approach equilibrium level of price from, for example, from above, the fact that they always overestimate it will make their learning process accelerate towards equilibrium. But when they reach it, since they don't know where equilibrium is, they need not necessarily stop there, and then they enter the zone where the sign of their expectation error reverses. Therefore, they start to update their equilibrium in the opposite direction, which actually gives rise to fluctuations. Also, a small remark that I said explicitly the assumption that we assume that agents do not know the equilibrium level. Well, there could be a different form of this assumption. We could say that agents know the equilibrium level, but they, as we said, perceive themselves to be too small to affect the economy, and if they know that the market is not going to stop at equilibrium, and if they predict that the market is going to move further, they will be better off if they will follow a forecast, even if they know the equilibrium level of price and output. So, as I showed theoretically how possibility of fluctuation can rise in the economy, we also did some simulations this. And here like comes an answer to the question, what about expectations? So this is one of the simulations. What we assumed is like the very simple learning tool. It just agents observe all the history of prices that they had before, and they apply and they build autoregressive model that best fits available data to them. And how they fit the model that best fits is just by using auto-RIMA function from like any statistical package. We just will every period when new data arises, agents apply auto-RIMA functions, give the best model with the best fit, use this model to predict one step ahead. This is how this works. And once again, I want to stress that in this model there are no shocks whatsoever. It's just basically purely deterministic process, and the plot you see arises just from being just from agents being, let me say, rational econometricians in terms of how Thomas Sargent was talking about that. Well, basically, how the simulation arises, we just say that in the very first period, agents believe that the actual price that's gonna come will be, for example, 1% higher than equilibrium price. But then, and then since in that case they obviously overpredict the price, the fun part starts. And we see that we model it for 300 periods, and amplitude of cycles reduced a bit over time, but still was still present there. What is also what is also very interesting to observe is that such a very deterministic model can cause what we call crises, because you can see a big drop in production at around period 170. Which just arise because agents. It's not proved formally yet, but our initial hypothesis is that like crises may arise when there is a radical revision of the model that agents use. So you see the vertical lines. Each vertical line shows point in time when agents just change the specification they use for forecast, and you can see that they do it pretty a lot. But these changes can be different. There can be like minor changes, so we like just throw or add one lag, or there will be like drastic changes when we like switch from AR to MA process, or like from AR to ARMA process, whatever. And the basic assumption is that once agents make a drastic change in the model they use, it may cause an economic crisis, or actually a boom on the other hand. So we did a couple of more simulations, and from what I told previously, one can get a feeling that these cycles in the long run will be necessarily converging to an equilibrium level, because like every time agents change the sign of error, but in the end, like common intuition says that most likely we should observe model converging in the long run. Well, it doesn't happen, because some simulations show that the behavior may be just like this. Once again, I want to stress that it's like purely deterministic from the way agents learn and from their expectations and make their decisions. That's how divergent cycles are possible. And what we were doing next was noticing that like auto-RIMA is very nice. Very nice way to model formation of expectations, and it gives some insight on model switching and what it means for the economy. Yes.
Can you describe briefly what sorts of initial conditions led to the closer cycles versus these? Do you remember?
Yeah, it's like I should have put parameters here, but it's around discounting rate is about like 0.8 or 0.9, and share of labor in production is about 0.6. This is basically only two parameters we had to assume, and we also like just twisted it a bit so that like just for simplicity, equilibrium level of output is 100 and equilibrium price is 1, just so it's like easy to observe on plots. And so, as I said, our theorem is pretty powerful. It's pretty interesting tool to model expectation formation. But on the other hand, it's pretty much impossible to study it formally, because since the agents can switch model in every period, it's very hard to formally deliver what will be the limiting behavior of the economy in the long run. So we also what we did, we also wanted to see what may happen if they if we fix the model agents believe them. We just say, okay guys, you believe that price follow AR2 process, and the only thing you can do is to update coefficients in this AR model. And by doing that, we also noticed a very interesting feature that this very simple model can show. It can show something called false equilibria. So what we did, we just gave initial beliefs in the parameters of AR2 model that lead to initial price to be around 20% higher than equilibrium price. And what we observed, that output started to fluctuate well below its equilibrium level, which is represented by a bold horizontal line. And then actually we noticed something like convergence to a false equilibrium when economy stands still at around our level of output at around 80, which is 20% lower than equilibrium level. And I didn't include the plot, but the truth is that this false equilibrium can be pretty much sustainable. If we did what we did, which I'm gonna say in the moment, then this level of around 80 would last for tens of thousands in periods with very slow convergence towards equilibrium. So agents update their beliefs, but probably with this particular set of parameters, the responsiveness of the economy is too low. Therefore, their parameters are updating too slow, and even over quite long periods of time, by how much they move towards equilibrium is negligible. They pretty much stay at output 80 for a long period of time. What we did to make them go back to the equilibrium was we introduced memory. We said in this particular simulation memory to be 300. So we said that agents build their models only on 300 points of data available to them, and they forget everything that have been before. Then, with introduction of this memory stuff, we see that models suddenly realize that they're doing something wrong, and they start moving back to equilibrium level at around period 550. I would say from the plot. But when they start to drastically too fastly move towards equilibrium, it causes a new wave of cycles, which over time converge. Actually, if you can see, they converge once again to some point a bit lower, just a bit lower than equilibrium level. What it illustrates is that economy can be pretty much feel pretty well without any incentive to. Okay, I should rephrase. The economy can end up producing much less than it could produce just because agents believe that's what they should do. And this is pretty much consistent with John Maynard Keynes' notion of animal spirits. So if they are set at low in the economy, they can be set low forever if not forever, but for for very long period of time if something doesn't happen. And what was another usefulness of introducing AR2 process was that we could actually start deriving some formal analysis of how the economy behaves, what will be the behavior of the economy in the long run. Would it be converging, diverging? Would it be at some wrong equilibrium for a pretty long period of time? And just for that, we can consider recursive least squares algorithm, which is well described in books on learning, expectations, and bounded rationality in macroeconomics. For example, Evans and Hankapohia, or even Thomas Sargent. Excuse me?
How do you choose AR2 model?
AR2 model was just, as I said, was just illustrative. So we derived main instances from our theorem, but then we said, okay, since our theorem is not being, we cannot study it formally, we just like want to pick up a model that we can study formally. We just like decided on AR2 just because it's a simple model.
Why is an Agnes cube not
Hmm.
one?
Okay, if you, it's actually, if you talk about, it's also we can talk about conditions for cycles, which we didn't derive yet, but if you make AR process, then you will not see fluctuations. Then you will see on this plot, if they start at some wrong point, they will just slowly converge towards equilibrium. So it's one of the conditions for fluctuations, that the model should be autoregressive process of at least order 2 for us to observe cycles. And that's basically what you see in both Paulson-Welson's multiplicator accelerator model, because it basically leads to equation for output which depends on previous two periods, t-1 and t-2, and when you do linear approximation of real business cycles model of Kydland and Prescott, they also come up with AR2 process. So coming back to that, I will not get into this math. I will just basically mainly skip this part. It just, we can get an equation of the form 10 which describes how parameters which are this big phi are updated, capital phi are updated over a small period of time in the economy, and therefore we can study whether when we take the limit of the thing, we can say whether the economy will be converging or diverging. So basically to say what will happen in the long run. If you are interested, I can come back to that. What is also what is important, that when for the sanity check, that once we establish this equation, it is easy to check that if we put equilibrium, like formula for equilibrium price level, then it just shows that parameters of the model that agents have should not change. That just means that they converge to an equilibrium. Now, as I promised you previously, I promised to talk a bit about possibility of monetary policy in the economy. And when we derive explicitly the equation for actual law of motion of total output, for total output, we can see that it has some fixed part and it has some changing part, which depends on the monetary base and depends on expected price. And what we also did, we just changed the subscript. So previously we had fixed money stock. Previously we had fixed money stock, and now we have some variable that may be affected by government. And actually, from simple model, we can see that monetary policy may have not effect even in the short run if agents completely know what is going to happen, if government publicly announces by how exactly it's going to change monetary base, and if they adjust their expectations in exactly the same proportion as monetary base is going to happen. Because in this case, you can see that in varying part of YT, any proportional change will just, if you multiply it by something, whatever, it will just cancel out. So for monetary policy to have short-term effect, it should be either in part unexpected, which is a very Lucas result, or agents should believe that changes in money stock for some reason do not imply exactly the same change in prices. So if, for example, money stock changes by 3%, agents believe that prices will change only by 2%. Well, if the first case is pretty straightforward, we got a quick look at the second case, more detailed look at the second case, and said, okay, can this belief that prices respond not one by one to changes in monetary place be sustained in the long run? So we assume that if agents believe that X% change in money stock would lead to psi multiplied by X% change in price level, basically we can show. I will just I'm running out of time, but we can show that this will not be sustained out from the learning perspective, because if agents believe that responsiveness of price is lower than 1, then the responsiveness will be always higher than they believe in. Then like what they believe in will not come true, and they will update the learning mechanism once again. Or if they believe that actual responsiveness of prices is higher than 1, then what will be the outcome in the economy will be lower than they believed in. So only psi equal 1 is sustainable belief of reaction of the economy to monetary base in the long run. So the conclusion is that monetary policy may initially have short-term real effects in the simple model, but they will disappear in the longer perspective when and if learning is complete. It may not be complete, so agents may actually never learn what is the reaction of economy to monetary base. So this is like these results from simple model are pretty disappointing from a point of view of central bank, because central bank is very happy to conduct monetary policy and see some real results of it, which the simple model is contradict. But it contradicts to it only because it is simple. Once we do a bit more complicated model, and we, for example, make households use hyperbolic utility instead of simple logarithmic utility, then the actual motion of output becomes a pretty nasty formula, which you don't want to go deep into detail. But the conclusion from it is that even if larger agents, the things do not cancel out anymore in this formula, and even if agents know precisely the upcoming changes in money stock and adjust their expectation right proportionally, still the actual outcome will be different. So this means that like introducing just a bit more complicated model will lead to monetary policy always have real effect. The question whether central bank is smart enough to foresee what exactly this effect will be is also remains open. But at least there remains a possibility for monetary policy. And to finish the presentation, I will just like quickly say what we're gonna do next. So we consider what we've done like pretty sufficient for our master thesis, but we would be pretty interested on working with it further. First of all, we need to polish what we have so far, bring to perfection what we did. Then we would be pretty happy to introduce generic analysis. So instead of assuming a Cobb-Douglas production function, instead of assuming logarithmic or hyperbolic or whatever utility, just assume like general functions like u and f. And it's of course way more professional and to derive conditions for fluctuations and more formal analysis from that perspective. We actually did some work, and something is coming out, but it still needs to be accomplished. Then we would like to build richer models. You saw that like our model is like very simple. It has no growth. It has no interest rate. The only thing that agents expect is price, which is very good and powerful for illustrative purposes, but it's probably not so useful to make real life predictions. And we would like to build models that would better, yet in such stylized and simple way, represent the real world. And as my co-author Nicola said, a really big step is between simulation and calibration, because yeah, we made some assumptions about parameters to see the simulations and to see how this model behaves from qualitative point of view. But it would be really nice to calibrate it to represent exactly the fluctuations in dynamics from the real world. I think I am done here, and thank you very much for listening.